Welcome to the workshop. Today we want to take a look at section 2.8, Bayes' theorem. And we'll start off by considering a motivational example. I think that Bayes' theorem for the most part makes pretty good intuitive sense. If I simply present it as its theorem though, then it would be a little bit confusing. So we're going to look at an example where we essentially use Bayes' theorem, and then we say, oh, hey, look, this thing is called Bayes' theorem. That's going to be our goal. So let's take a look at this motivating example or intuitive example, whatever you might like to call it here. So a mail order house employs 3 stock clerks. So first of all, what's a mail order house? Essentially what we're thinking of there is, you can think Amazon. So somebody sends in an order, employees run around, grab all the items for the order, put it together and ship it out. Okay, so a mail order house employs 3 stock clerks, Larry, Mo, and Curly, who pull items from shelves and assemble them as a package, right? Put it together in a box, whatever, for subsequent verification and packaging. Excellent. So maybe they don't put it in the box. Maybe they just gather it together, send it somewhere else to be verified and packaged. All right. So Larry makes a mistake in an order 1 time in 100. Mo makes a mistake on an order 6 times in 100, and Curly makes a mistake 2 times in 100. So if Larry, Mo, and Curly fill respectively 25, 35, and 40% of all orders, what is the probability that a mistake will be made? Okay, so we don't have here direct information. We have some ideas. We know how often Larry makes a mistake. We know how often Mo makes a mistake. And we know how often Curly makes a mistake, but we don't have explicitly how frequently a mistake happens overall. And that's what we want to find. And it essentially works out to be that since the only way that a mistake can be made is by Larry, Mo, or Curly making a mistake, then we effectively have the information we need to discover the probability that a mistake is made. So I want to start off with a few events, and I'll write those up here. So let's let L be the event that Larry Larry fills the order. Excellent. Let's let M be the event that Mo fills the order. And let's let C be the event that Curly fills the order. Okay, we would also like to have, let's see, let W be the event that an order is filled wrong. So it's phrased as mistake in the problem, but M is being used. So let's let W be the event that an order is filled wrong, right? A mistake is made. All right. So how can we have a mistake in an order? Well, wrong item or wrong quantity. So Amazon ships you the wrong item, or they send you 1 instead of 2, or 5 instead of 3. It happens. All right. So what we want to think of it as, if we want to draw a Venn diagram, and let's let this Venn diagram be, right, this is all orders that are being filled. Well, they're either filled by Larry, they're filled by Mo, or they're filled by Curly. So this is our sample space, and we have 3 separate events, right? And so instead of circles, I want it to fill up the whole thing. So all orders are filled by Larry, Mo, or Curly. Now, if we wanted to say, all right, well, we make mistakes. or they make mistakes, right? So we want to find the probability that that a mistake is made. So we're looking to find this area here, but that can be found by considering the area in 3 separate pieces. So we could consider Larry's contribution, and then we could consider Mo's contribution, and then we could consider Curly's contribution. So if a mistake is made, it's either made by Larry, Mo, or Curly. So we just want to find these 3 probabilities individually. So we want to find the probability that we have a wrong order, or an order is filled wrong, right? A mistake is made, is the probability that we have, let's see here, it's wrong and Larry filled it, plus the probability that it's wrong and Mo filled it, plus the probability that it's wrong and Curly filled it. That's what those 3 areas are. But still, maybe this isn't quite quite piecing together yet. So let's give one more nice visual representation of what's going on here. This is kind of fun. We can make a tree diagram for the situation. So let's say someone submits an order. All right, once an order has been submitted, that order will either go to Larry, Mo, or Curly. Okay. Now we're only considering what happens, or the situation where an order is filled wrong. So Larry fills it and it's wrong. Mo fills it and it's wrong. Curly fills it and it's wrong. So we end up with 3 different scenarios for this. So okay, we can start filling in some probabilities, but these are my 3 scenarios. Once an order is submitted, either Larry, Mo, or Curly are going to fill it. All right, so we go from there. Well, the probability that Larry is going to fill it is given by, right, he fills 25% of the orders. Mo, the probability that Mo filled it is given by 0.35, since he fills 35% of the orders, and the probability that Curly filled it is 0.40, because he fills 40% of the orders. Excellent. Now, what's the probability that it will go along this path, or that we would follow this path? The probability would be given by, well, we're looking at the probability that Larry filled it, and we're going to get a mistake, but not and, right? We're traveling from Larry to the mistake here, so the probability that it's wrong given that Larry filled it. And we're actually given that number, right? Larry makes a mistake 1 time out of 100. So what's the probability that we're going to travel along this edge? Well, this would be the probability that there is a mistake given that Mo filled it. And then the probability of us traveling along this edge, this would be the probability that we have a mistake given that Curly filled it. So Mo makes a mistake 6 times in 100, and Curly makes a mistake 2 times in 100. Okay, so this gives us our probabilities, and the end result is that Larry filled it and we have a mistake. So that is going to give us, right, once we're here, we can identify the probability that Larry fills it and there's a mistake as the product of these 2 numbers. What's the probability that we're going to go down both of them? Well, the product. So probability of Larry filling it times the probability of a mistake given that Larry filled it. But this should actually look really familiar to us. let's see here. I think this is in section 2.6. Let me take a look here a moment. Yep, that's conditional probability. So we have the multiplication rule, the probability, right? This is theorem 2.9. So we are observing it here on a tree diagram, but this is theorem 2.9 that we're actually using in each of these. So the probability that Mo filled the order and we have a mistake is the probability that Mo filled it times the probability that there's a mistake given that Mo filled it. And the probability that there's or that Curly filled it and there's a mistake is the probability that Curly filled it times the probability that there's a mistake given that Curly filled it. Excellent. So these three ways are the only ways that we can get a mistake. Larry fills it, he makes a mistake. Mo fills it, makes a mistake. Curly fills it, makes a mistake. So I've said the same thing 2, maybe 3 times now. So hopefully it's at least sank in a little bit. Take a look at it again, think it over. If you're not quite following along, feel free to pause and go back. Okay, but if we want to find the probability of a mistake being made, then again, all we have to do is consider the sum of the 3 ways that we could do it, or consider the sum of the probabilities based on our Venn diagram, this sort of a thing. This is clarified further by this, very convenient in our tree diagram, or simply theorem 2.9. And this would give us that the probability of a mistake is equal to, let's see here, we said it's the probability of a mistake and Larry fills it plus the probability that we have a mistake and Mo filled it plus the probability of a mistake and Curly fills it. But that, of course, is the probability that Larry filled it times the probability that there is a mistake given that Larry filled it plus the probability that Mo filled it times the probability that there is a mistake given that Mo filled it plus the probability that Curly filled it times the probability that there is a mistake given that Curly filled it. All right. We know what each of these are. We said that the probability that Larry filled it was 0.25. The probability that he makes a mistake is 0.01. The probability that Mo gets it, we said, was 0.35. The probability that he makes a mistake is 0.06. And the probability that Curly gets it is 0.4 times the probability he makes a mistake is 0.02. Okay, let's see here. We perform these calculations and we get 0.0315. So we can finish this off by answering the question that was asked. The probability that a mistake is made is 0.0315. Or 3.15%, right? What are the chances? The chances are 3.15%. Would be a fine way to say that as well. All right. Whew. That was a bit of work to get us there. But I think that what we've done with how we showed it, the computation is fairly intuitive, okay? It may not have been obvious, but now that it's been presented, hopefully you're saying to yourself, of course, that makes sense. So with that in mind, in the next video, we'll take a look at the theorem and one more example. So 2 examples essentially of the theorem, this one and the next one with the theorem in between. So I'll see you guys back in the workshop in just a minute.